Welcome and hello. This is a video exercise in the FHWA hydraulic toolbox. And what we're going to be dealing with is riprap and bridge piers. So we're going to be determining which riprap class should be used for the different piers you're seeing on the screen here in this diagram. Find the riprap class for each bridge pier. We're given some channel data, as well as channel geometry and dimensions, as well as some pier data. So we're going to be using the channel calculator to determine the flow rate and velocity. And then with that data, we're going to create a riprap calculator, one for each of our two piers. I've got these labeled pier number 1 and pier number 2. All right, so go ahead and take a screenshot or remember these numbers because we're going to be using them in the calculator. I'm going to minimize that and head over to our calculator. We've got this project called Salmon River, just a hypothetical project name. And then right click, add a new channel analysis. So I'm going to also rename this channel analysis calculator channel at bridge 1. So we'll say there's a bridge 1 that crosses Salmon River at a specified location, river station number, whatever. I'll just call it bridge 1 though. And then let's open that up. So what we see from the cross section is we have a 1-to-1 side slope. It's labeled right here, but that 1-to-1 side slope is meant to be for all of the side slopes. And we have a Manning's roughness coefficient, a longitudinal slope, as well as a irregular shaped cross section. So let's get to work on creating that channel calculator. I'm going to click on for type, select cross section. So this is where we get to manually enter the cross section data. Click on define. And now let's get that cross section up on screen again. All right, so I have my cross section over here, and I've got my station and elevation values in this table over here to the left. The number of points we're going to use is 1, 2, 3, 4, 5, and 6. So instead of 3, I'll type in 6. Click tab. Now I have 6 rows in my table. We'll start at station 0. So station 0 is right here, and then we'll work our way to the right with positive stationing numbers. And then we'll also have to make up some elevation values as well. All right, so let's start with station 0. That's right here. If this is, let's see, the water depth is 8 feet at pier 1, and then the water depth is 4 feet at pier 2. So we'll just go ahead and make up an elevation right here. We'll say there's maybe 2 feet of freeboard for a total 10 feet, and at 1-to-1 slope, that would be a 10 feet run in the station. So this would be 10. Then let's just go ahead and label all the station values first. So plus 60 would be 70. Enter. And then we're going to go up 4 feet at a 1-to-1 slope. So that's a run of 4. Plus 70 is 74. And then plus another 60 to 74 would be 134, which is there. And then finally another 6 would be 140. All right, so that's our station values. I'm going to arbitrarily set the elevation of this Thalweg location, the base of Pier 1, as about 20 feet. Doesn't really matter as long as we're consistent with our elevations. 20 feet plus 10 feet up to the lower chord of the bridge deck. That's the vertical elevation would be 10 feet because it's a 1-to-1 slope, 3, 0 for 30, which means the last 0.6 would also have an elevation of 30. And then points 4 and 5 right here, which represent the same elevation as the base of Pier 2, would be, let's see, it would be 20 plus 4, so 24. Type that in right there. All right, that's good. The Manning's N coefficient, we were given that as 0.035. Okay, so let me just move this back over here. And 0.035, I'm going to just copy, paste, 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 paste. So it's the same for the entire section. The channel slope we were given as 0.5%, so 0.005 is the decimal, and click OK. All right, so that is all done. We know the depth here is 8 feet, and on it, it's in meters. So let me go ahead and switch that to metric units. And then let me go ahead and save it as well. I'll call mine project 2 and click on save. Okay, let's go ahead and make sure that the numbers are correct with the US customary units. So cross section, that's correct. Define. And of course, they're not correct. Oh, let me fix these. Okay, there we go. That's corrected. The slope and Manning's N are still good. Okay. And then the depth, this is going to be 8 feet. So I'll click on calculate. And then here is our design flow of 7,331 CFS. Looks like our average velocity calculated out to 9.35 feet per second. So these are some terms that are going to be used in the Riprap calculator once we assign it to use this channel at bridge 1 channel calculator cross-section data. Okay, so click OK. We're done with the channel calculator. Now let's go right click and add new Riprap analysis. I'm also going to rename this and just call it Riprap at bridge 1. And then I'm also going to call it dash pier 1. So I'm going to have a separate Riprap calculator for each pier. All right, so I'm going to double click to open that up. For the structure type here, I want to select pier, bridge pier. And then for the channel parameters, I'm going to select channel at bridge 1, that channel calculator. Now we have some of the same calculation results popping into place. 7331 for the flow rate. The channel depth is 8 feet. Well, yeah, bottom width and side slope aren't showing up here because it's probably expecting to be like a trapezoid or a rectangular shaped cross section. So this should be correct though as far as area and top width. Next, what I want to do is click on this button to transfer values from the channel calculator. Okay, it looks like that was done already. The average channel velocity at the bridge is 9.35 feet per second, so that's correct. Some of the other parameters I need to put for my here data is here number 1 is using a 1.1 for the velocity adjustment factor. Both the piers are 6 feet wide and have a round nose shape. So let's go ahead and add that data in. The velocity adjustment factor is going to be 1.1. The pier shape here is round nose. That's correct. And then the pier width, normal to flow, is going to be 6 feet. Okay. Now, I didn't specify anything for contraction scour depth or form depth, so I'm just going to assume that's 0 feet, even though in reality it probably would not be 0. And specific gravity of the riprap, again, I'm just going to assume the default values. All right, we're ready to check out some of our results. We calculated a design velocity of 15.43 feet per second, and then the D50 size was calculated at 472 millimeters. So the smallest riprap class that is larger than D50 equals 472 is class 6 right here. The D50 for class 6 is 546 millimeters. And again, that's the average size for that particular range of riprap. And then further towards the bottom, we actually have numbers that are associated with the layout of the riprap at that particular bridge pier location. So even though we have the riprap class size, knowing exactly where it should be laid out with respect to the pier is what this layout section gives us. The different dimensions for the depth of riprap, that's variable T. We'll see the figure in just a moment. I'll bring that up. And then minimum riprap extent and filter placement extent. You see a reference here to the Hydraulic Engineering Circular number 23, figure 11.15. This is a PDF document, which I will leave a link to in the description, but I also have it available right here. This is the 376 pages, and on page 213, this starts chapter 11, where we talk about the riprap at bridge piers. And if I scroll down to page 227 right here, this is a diagram, figure right here, figure 11.15, riprap layout diagram for pier scour protection. So if I scroll up here, this variable represents the width of the pier, which for us is 6 feet. The direction of flow is left to right. And then this 2A here represents the riprap placement. So 2 times the width basically from the edge of the pier in all 4 directions. That would be 12 feet. And that is the 12 feet we're seeing right here, the minimum riprap extent. So it can be more than 12. This is just 12 feet is the minimum. And then there's also this filter placement, which is 8 feet. I believe this is 2/3 times the minimum riprap extent. That filter placement, if we scroll down, oh, here we go. So here is the 12 feet right here, and then the filter is 8 feet. That'd be extending out from the pier. And then this T right here, this is the thickness. This is how deep the riprap should be beneath the soil surface of the riverbed. So that is this dimension right here. It's in inches, so 64 inches is what, 5 feet 4 inches? Depth of riprap below the stream bed. design thickness of riprap below the stream bed. So anyway, those are the answers for our Pier 1. We have the D50 size requiring class 6 riprap, and then here is the layout of that riprap. So I'm going to click on OK and then save. Now, what I want to do now is create a second riprap calculator, but for Pier number 2. Now, in reality, the velocity would probably be a little bit higher for Pier 1 than Pier 2. But for this exercise, I'm just going to use the velocity that was calculated in the channel calculator. So I'm going to be using the average velocity. But otherwise, the only difference between Pier 1 and Pier 2 for this exercise and this analysis is the velocity adjustment factor. We're going to be using 0.9 instead of 1.1. So let's go back to make a copy of our riprap calculator, duplicate, and then I'm going to rename and then just change it from Pier 1 to Pier 2. Double click to open up the calculator and then change this 1.1 to 0.9 and then tab off. And then everything else should be the same. I'm making some checks. The velocity looks good. The flow rate looks correct. And if I scroll down, it looks like class 3 is the requirement for Pier number 2 because the minimum required D50 is 316 millimeters. That's just a little bit more than a foot. And then 317, yeah, just barely fit in the class 3. So even a slightly larger D50 would probably bump up the requirement to riprap class 4. As far as the layout goes, it looks like we have the exact same minimum riprap extent and filter extent. However, the minimum riprap depth has decreased quite a bit. Now it's only 37.5. All right, well, that's it for this exercise. What we did was investigate the riprap requirement on a bridge for 2 different bridge piers using the riprap calculator in the hydraulic toolbox.